Hello gentlemen, welcome to our video on section 10.3 called gas laws. Now in this chapter we're going to be studying the physical conditions of gases and physical properties of gases. And in order to do that we need to look at four variables. Those variables are temperature, pressure, volume, and the amount of gas, which means number of moles of gas. Now there are different laws that help us study the physical conditions of gas and how they relate according to temperatures, pressures, volumes, and number of moles. The first one to take a look at is called Boyle's law. Now, Boyle's law looks at the relationship between pressure and volume. But to make things simpler, we hold things constant. So we look at pressure and volume when the number of moles is held constant, so we have a fixed amount of gas, and the temperature is held constant. That allows us to look at pressure and volume a little more closely. All right. So the law is that as pressure and volume change from one scenario to the next, so if I had a pressure and volume here, and then I were to change something and get a new pressure and volume, it would be an inversely proportional relationship. So as pressure goes up, volume goes down. Or as volume goes up, pressure goes down. They're inversely related. The equation that defines this is P1V1 equals P2V2, where P stands for pressure, so we have an initial pressure and an initial volume. If you were to change that initial pressure to P2, your volume V2 would change as a result of it. We'll do some problems with this formula later on. It's not very difficult, it just looks very new to us right now. So the biggest thing is what I box here. It's an inversely proportional relationship, where the product of the initial scenario equals the product of the final scenario. Another law is Charles's law. So Charles's law shows us the relationship between volume and temperature. But again, it's easier to look at this when something is held constant. So in this particular law, we're going to have pressure being held constant, and we're going to have a fixed volume. A fixed amount of gas is being held constant. So let me back up there. Fixed amount of gas. So when the amount of gas is fixed, meaning moles is fixed, and pressure is constant, volume and temperature will have a directly proportional relationship. And this one should make sense, right? So let's think about if you're going to heat up a balloon or heat up something that has air in it, right? When you heat it up, that balloon inflates more. It expands its volume. But if I were to put a balloon in like the freezer, that cool temperature, that lower temperature, would make that balloon shrivel up and the air condense. So this is just saying that volume and temperature have a directly proportional relationship. And in mathematics, directly proportional relationships would be this relationship based on division here. So we have V1 over T1 equals V2 over T2. So if you have some initial volume and temperature, and then you were to change the temperature, let's say, your volume would then adjust based on that temperature change. So this is Charles's law. One thing to note about Charles's law, or any law that involves temperature, your temperature must be in units of Kelvin, not in Celsius. So if you are given a temperature in degrees Celsius, we know how to, handle that. We take our temperature in degrees Celsius and we add 273 to it to get to Kelvin. Now another law is called the Gay-Lussac's law, so by Joseph Gay-Lussac. This illustrates the relationship between pressure and temperature. And of course, we're going to hold some things constant here. So when we hold volume constant and the amount of gas constant, so we say fixed mass or fixed number of moles, fixed amount of gas. When we hold that constant, pressure and temperature are directly proportional. You can think about, again, kind of like a sealed container. If I have a sealed container of, certain number of moles, and obviously if it's a fixed container, then the volume's fixed. If I increase the temperature, the pressure is going to increase. Thus, well, we have a directly proportional relationship. And that's given by this law here. Okay, our next law is called the combined gas law. Now, the combined gas law, there's a lot of writing here, guys, and no need to make it complicated. It's just taking the laws we've looked at and putting them together. So we take Boyle's law, Charles's law, and Gay-Lussac's law and put them all together, and we get the combined gas law. And it's here. Because we can't always, in nature, keep things constant. We can control it in a laboratory setting, but it becomes more realistic when we don't keep things constant. So this is if we have a certain pressure, a certain volume, a certain temperature of some kind of scenario, and then those things begin to change. So my pressure changes, my temperature changes, what's the new volume? Or my temperature changes, my volume changes, what's the new pressure? So we find variables based on what changes from the first scenario to the second scenario. Of course, what you don't see here is number of moles of gas, because here moles are constant, they're fixed. Now, our last law is the ideal gas law. So the ideal gas law is not more complicated, but it involves a few more things. So I'll do a little breakdown of the ideal gas law, which we see is PV equals nRT. Let's talk about where it comes from and what the word ideal means. So Boyle's law we had that the volume and the pressure were inversely proportional. So there's a way to kind of write that. I'm going to write it from the perspective of volume. So volume is inversely proportional. So there's a symbol for proportions, and that's this symbol here. It's the Greek A, right? So alpha, the alpha symbol, or it looks like a little Jesus fish, however you want to think of it, right? And inversely proportional means they are going to be inverse in that fraction form. So that means volume is inversely proportional to the pressure. So as volume increases, pressure goes down, vice versa. And this is when number of moles, which is N, and temperature are constant. Now, Charles's law. This was saying that volume is directly proportional to temperature. So there's no fraction there because it's directly proportional. Moles and pressure are constant. And there's a law that we actually haven't talked about today because there's really no major need for it right now. But it's Avogadro's law, which, just like many of the other laws, is just showing how things are related. And Avogadro's law says that volume is directly proportional to number of moles. So as volume increases, moles increases. As volume decreases, moles decreases. And in this one, pressure and temperature are held constant. If we combine all these laws, we get volume is proportional to N times T over P. All I did was just take all these and put them together. Now, we can't deal with proportions in a definite manner in chemistry. We have to make this proportion something that we can actually use, like an equation. So there is something called a proportionality constant. That helps relate all of these things, the N, T, P, and V, all together. And that proportionality constant, we call it the universal gas constant. Which has the symbol of R. And the number of this constant is 0.08206. In the units are the units of all those variables to the left there. Atmosphere, liter, sorry, there should be no comma there. There's no comma there. Atmospheres times liters per mole times Kelvin. Those are the units for volume, moles, temperature, and pressure. So that ties them all together. So if I incorporate that, I get this. V equals R N T over P. You just put the R there. This is oftentimes rearranged as PV equals nRT. So it's called, we can sound it out phonetically, PIVNERT, and that helps you remember it, PIVNERT. All right, so that's the ideal gas law. It's relating pressure, volume, number of moles, and temperature with the presence of this universal gas constant. And there are your variables below. That's the ideal gas law. Now, the word ideal. Ideal means, of course, in a perfect scenario, if everything was amazingly perfect. We don't live in a perfect world, not even in nature, right? So ideal gas isn't really a thing. It's close, it's just basically making our job easier to study it. An ideal gas. The gases on this planet, they're real gases. So the difference between a real gas and an ideal gas is kind of hypothetically perfect scenario, meaning we make some assumptions. So one, an ideal gas that we assume the molecules of the gas do not interact with one another. Meaning we assume these gas particles don't touch each other. They don't touch the container, they don't touch anything. Because when they do touch the container, do touch one another, that's going to alter how we have to look at moles, temperature, pressure, and volume. So we're making some assumptions to assume ideality. So we assume that the volume of the molecules is so small, it's negligible. So the actual gas particles themselves, we're assuming that there's no difference between, the gas particle for nitrogen and the gas particle for oxygen in terms of volume. We're assuming that their volumes are just negligible because they're so small. But in real life, that's not true. In real life, different gases have different sizes in terms of the actual gas particles themselves, and that can have some influence, of course, on the volume up here in our calculations. So assuming that these two things are true, we can make it an ideal gas and just use this simpler equation. If we're talking about real gases, if you're, a gas chemist, if you're studying, it is a gas chemist, but if you're studying gases as a chemist, then you cannot really assume steps 1 and 2 here. You have to deal with the real gas scenarios. Okay, so let's look into how to actually calculate and use this. So when you're approaching a problem on gas laws, there usually isn't a heading that says, hey, this is the ideal gas law. This is the combined gas law. Use Boyle's law. You have to use what's in the problem to help you figure out what law to use. So let's read the first one. A sample of chlorine gas occupies a volume of 946 milliliters at a pressure of 726 millimeters of mercury. Calculate the pressure of a gas if the volume is reduced at a constant temperature to 154 milliliters. So let's write down what we have. The way you figure out what you're going to use, what law, is by writing down your knowns and unknowns. So this sample of chlorine gas has a volume initially of 946 milliliters. That pressure at the volume, at this particular volume, is 726 millimeters of mercury. It then says, sorry, that should not be a P2, that should be a P1. And then it says calculate the pressure, so it's a new pressure, P2. Calculate the pressure if the volume is reduced to 154 milliliters. And here's where it's good to be able to check your answer, right? Knowing the logic. We know that Boyle's law has an inversely proportional relationship. So here, if the volume is going down from 946 and reduced down to 154. So the pressure, being inversely related, should go up. So it should be something higher than 726 millimeters of mercury. But since we have volumes and pressures, we know we're going to be using Boyle's law, which is P1V1 equals P2V2. If I rearrange this, we're solving for P2, that's going to be P1V1 over V2. So now we just fill in, right? There's no temperature to convert here, so we just fill it all in. P1, 726 millimeters of mercury. V1, not V2, over, now V2. Milliliters cancel, leaving you with pressure units, which is what you want. And there we go. That's how you do a Boyle's law problem. This is very similar to, dilution. M1V1 equals M2V2 from chapter 4. All right, another example. A balloon inflated in an air-conditioned room at 27 degrees Celsius has a volume of 4 liters. It is heated to a temperature of 57 degrees Celsius. What is the new volume of the balloon if the pressure remains constant? Okay, so we have constant pressure, and we have a temperature of 27 degrees Celsius, and there's a volume of 4 liters. It's heated to a new temperature of 57 degrees Celsius, and we want to know what's the new volume. Okay, here we have volumes and temperatures. That's going to be Charles's law, which is V1 over T1 equals V2 over T2. They're asking us for the second volume, so V2 would be V1 times T2 over T1. Now, before we start plugging in numbers, we have to think about what I said about temperature. Temperature must be in Kelvin. So let's convert that now. We add 273 to both. So 273 plus 27 is 300. The sig fig rules here. It's ones place. So this ones place is significant, meaning we put a dot there representing that all three of those are significant, all three numbers, the 300. 57 degrees Celsius plus 273, that's going to be 330. And the same sig fig rules there. So now we just plug and chug. So V2 equals V1, so V1 is 4 liters, times T2, which is 330 Kelvin, divided by T1, which is 300 Kelvin. Put my dots there. So V2, 4.40 liters, because Kelvin cancels. That's our answer. Let's try another. An aerosol can with a volume of 325 milliliters contains propellant gas at 445 kilopascals and 12 degrees Celsius. What volume would the gas occupy if it was allowed to escape at 101 kilopascals and 21 degrees Celsius? So here, I initially have a volume of 325 mils, a pressure of 445 kilopascals, and temperature equal to 12 degrees Celsius. That's what I have initially, so I can put ones there. And then it says, what volume would the gas occupy? So if the volume changes, what would that volume be if you change the pressure to 101 kilopascals and you change the temperature to 21 degrees Celsius? Okay, so this is going to be the combined gas law. We have 3 variables. And the combined gas law, if you remember, is taking Boyle's law, Charles' law, and Gay-Lussac's law and put them all together. Now we have to convert the temperature before we can do any math. Plus 273 here. It's 285. Plus 273. That's 294. Okay, so we're solving for V2. So if we're solving for V2, that's going to be P1 V1 times T2 over T1 times V2. Oh, not V2, P2, not V2, sorry. There we go. Okay. So now we can plug in 445 kilopascals times V1, 325 mils, times T2, 294 Kelvin, divided by T1, 285 Kelvin, and P2, 101 kilopascals. V2 is 1480 milliliters. Last one. A rigid steel cylinder with a volume of 20.0 liters is filled with nitrogen gas to a final pressure of 2 atmospheres at 27 degrees Celsius. How many moles of nitrogen gas does a cylinder contain? Okay, so now they're asking us for moles. There's only one equation that's featured moles thus far. So we've got volume, nope, not milliliters, liters. We've got a pressure. We've got a temperature. And they're asking for moles. All right, so this is going to be the ideal gas law. That's the only equation that actually features moles, so we know to use that. But of course, we have to include the proportionality constant or the universal gas constant. So R is 0.08206 atmosphere times liter per mole times Kelvin. Okay, and we're looking for N, so we solve for N. It's going to be PV over RT. So now we plug in. So my pressure is 2 atmospheres times my volume of 20 liters divided by R, 0.08206 atmospheres times liter per mole Kelvin times your temperature. If we simplify that, we get 1.62 moles, and this is nitrogen gas, so we can put that there. Now please make sure your units all match that of R. So R has atmospheres, liters, moles, and Kelvin. So if you're given a pressure and your pressure wasn't in atmospheres, you need to convert it to match R. If your volume wasn't in liters, you have to convert it to match the units of R, which are liters. So remember that. You're always converting to match atmospheres, liters, moles, Kelvin. This problem made it easy for us and gave us everything in the right units except for temperature. But that's how you would do this. Gentlemen, take notes. Come prepared to do a little bit more practice on this. Hopefully the examples here helped. Adios.